participants, we are about to start the webinar. The speaker for today is Professor Catherine from National University of Taiwan. She took her PhD from Illinois University, USA. After that, she worked in South Korea for some time. And then in 2009, she joined the National University of Taiwan, Singapore. And she is a winner of PLS Young Engineer, Outstanding PLS Young Engineer Award. She is award winner of that. And she is also now in charge of the Women in Engineering of Power Electronics Society. So with this, I request Catherine Madam for her presentation. Madam, it's over to you, Professor Catherine.
Hey, thank you very much for the introduction, and again for having me. It's an honor to be presenting today, and I'm very impressed by the very big turnout from your chapter. So I'm very excited and hope I can share some information with everybody. So I guess I'll get into it. So today I'll be talking about some of the research I've been doing on what we call differential power processing, and these are DC-DC converters, and I'm specifically looking at solar photovoltaic applications. First, I wanted to give you a sense for where I am. I'm in National Taiwan University, which is in Taipei. And originally I'm from the US, as was mentioned, and I also taught some time in Korea. So I've traveled a little bit around and have been doing power electronics for a number of years. So I'm hoping to get a lot of interesting things for you to learn about. If you ever get a chance, in the future, when travel is more possible, I invite you to visit National Taiwan University. One of the very nicer pictures is shown here on the right. It's a beautiful campus in the city, but also has a lot of nature on the campus. So you're all welcome to visit if you have the chance. I run the PARIS lab, is what we call it for short, in order to remember it more easily. It's a Power Electronics for Advanced Renewable Systems lab. And we have a small group doing power electronics at NTU. And I have a few different areas of research. My main ones are, one, improving grid connected solar PV power. And I'll be talking a little bit about that today. We design and manufacture boards, and then we'll test them using various systems. And we specialize in PV emulations using a certain hardware setup. And we also do some simulation and then outdoor experiments and testing. Another area that is an emerging area for our group is enabling portable PV power. So not just the ones on the roof, but also looking into smaller applications and seeing if we can put photovoltaics on things that are movable, for example, wearable electronics or small vehicles or other things. So that's another area where we're trying to apply the concepts of differential power processing to new emerging applications. So if you're interested in that, I encourage you to look at some of my website and some of our work. In this talk, I'll be talking about some reliability challenges first, and then that's a motivation for while we're looking at PV differential power processing. And I'll use PV, sometimes that's photovoltaic, so solar cells usually. And if I say DPP, that means differential power processing. And I hope that will give you definitions for the terms that I'll be using. Then I'll go into some of the topologies that you can implement these ideas. And then I'll talk about a specific type that I've implemented in my lab and some of the results from that. So let's start with the reliability challenges. And we're looking at specifically series connected PV cells. So this is more of the traditional approach. And we're gonna start at the PV panel level. So if you see a PV panel, you usually see all the little squares. And so those are the PV cells themselves. And each of those is a pretty low voltage. I'd say it's around one volt plus or minus some depending on the material. And in order to get to the higher voltages that you need for grid, which is usually anywhere from 120 to 220 RMS, then you need to put them all in series. So the panel usually has the cells connected in series. So you can see following this orange dotted line, the cells will go in series like this. So the first two columns will make up one series string. And then you have 2 and then 3. So usually you have 3 of these substrings in each of the panels. And you can kind of represent those substrings here. So each of these would be, for example, this column here. And usually we have a bypass diode that goes on the outside. And these are all located in a junction box that's behind this PV panel. So I don't show it here, but right where the mouse is where the junction box is. And there is a lot of things that we have to worry about in the construction of these, and I'm specifically going to talk about mismatch, so the problem of mismatch in our system. So that's the basic construction. Now let's go into some mismatch problems that occur. So ideally, you would have all of these cells are exactly identical. So you would manufacture them, they would be exactly the same, and you put them all in one panel. However, when you're manufacturing these, this PV cell is essentially a large diode. And so it's a very large area and it's difficult to get them completely uniform. So when you manufacture them, you're going to get some tolerance in terms of the power. So maybe one cell will produce, here's an example down here taken from, I think from SunPower is one of the companies that makes them. Maybe one cell is very low power, 3.4 watts, and another one's very high, so 3.8. In order to reduce the variation between cells, the manufacturers will bin them. So usually they're done in person, and someone will actually measure each of the cells and then bin them into similar groups. So for example, in one panel, so this is an example down here in the graph, the 335 is a power in one of the panels. So this is a model number for one of the panels, and it provides 335 watts. And the identical panel, essentially, except for the PV cells are from a higher group of power, that one provides 385 watts. So if you ever see panels, they look exactly the same, but they just have different panel power levels, that's usually a result of binning. So they do that to get rid of the mismatch between the different cells in series. So a lot of effort is put in at the manufacturing level to get rid of as much mismatch as possible. But even with binning, you'll see you may have a range of power that's maybe varying 1 watt, for example, between the same cells in a panel. So that's one source of mismatch right from the beginning, even brand new cells. And then once you install them, you still have problems such as dusting. So shown in this picture on the left, once they've been out for a while or just some weather events, you'll get dusting over the panel. And you can see they're pretty thick on those panels, for example, and that will, one, reduce the amount of sunlight hitting it. So it reduces its performance, which is not good. But also you'll see they're a little bit uneven in terms of the dusting or the sanding on top of the panel. So that will also create some mismatch between the panels in the system, the cells and also the panels. One way people can try to reduce that is if you have a large solar farm, they may have a cleaning solution. So you may have little robots that clean, or you may just people physically clean them every once in a while. But that takes a lot more effort. In short, people are trying to reduce the mismatch as much as possible. So why is this a problem? What's wrong with some mismatch? Well, one problem that happens is called hot spotting. And this is a little bit more extreme. One will be just you're going to lose power, which we're going to discuss in a few slides. And then the other one is that when they're uneven, they can actually, some of them can become weaker. So these cells that are heating up are actually weaker than the cells around them. And the power from the other cells essentially gets pushed through these weaker cells, and it causes them to heat up. So they actually become a load rather than a source. And these panels I took this myself on a rooftop in Texas a few years back, and these were shorted, so they would be in the bypass mode, for example, which is a normal operating mode. It can happen. And if that's the case, then you can see that some of these cells become hotter. And it's not just one point in the cell, it's the whole cell. So this appears to be a result of variance in the panel, in the cells themselves. So those red ones, for example, this one gets up to 35 degrees Celsius, or 34, is much hotter than the rest of them. This heat may start to degrade the material, but it will also, the PV material itself, but more rapidly is it will heat up the encapsulant if it gets to very high temperatures, and it can actually burn through the encapsulant or damage the encapsulant. And then things like the environment, salt, weather can come in and cause corrosion and also start to degrade the panel. So these are all things that you want to avoid as a owner of these systems. You want them to work as long as possible and provide as much power as possible. And just to give you a sense for how quickly these will occur, they say, oh, does this occur very quickly or does this take a long time? Here's a video of a PV formation, PV hotspot formation, and we did this by doing partial shading. And so it's hard to see because it's an infrared image, so we're just seeing the temperatures, but this is a newspaper that we rolled up and used to cover part of the panel. But you can see in less than 30 seconds, we're already starting to see some heating up of this panel. So this is a hotspot forming in just a couple minutes. This was not an extremely hot day, but you can still see that this one area is becoming hotter. So this is something that happens with the cells, but because we don't usually see them in IR, we don't see this, it just looks like a panel to us. We don't see this kind of damage that may be occurring internally, which can degrade the system. So this is a result that can be a negative result with mismatch in the system. Other ways to have mismatch is the one actually that's most common, which is partial shading. And I have an unusual example of partial shading. So usually you can have, for example, leaves or a bird or a bird nest, things like that, or dusting that can be uneven on the panel. Here's a more interesting example of a goat that's on top of the panel and creating some partial shading. So we're going to use this as an example to go through what's happening inside the string when partial shading or degradation or mismatch happens. So let's go back to an example where we're looking at this 3 substrings put together, and we have something shading one of them. So this is creating a shadow over part of this string, and this red one is where, for example, the hotspot may occur. And if the shading is really severe to the level where the amount of current that could go through it and produce power is really low, much lower than the ones around it, what happens is that the overall current will be higher. So the extra current, it needs to take more current than this PV can provide. So some of the current will go around this bypass diode, but you'll still have current going through the string. It will just be limited. It won't be a very high amount. The rest of it will go through the bypass diode. So let's go a little bit deeper into the electronics of what's happening. So the IV curve. Ideally, everything would be the same. So this is, if everything is exactly matched, then we would have just the string current going through here. So this is in series, so all of them, the string current is only one current for your system. And let me explain this really quickly. So this is the IV curve for a PV. It's a drawn one, but shows there's this knee of the curve, and it is kind of a sloping. It has a positive value. So this region here, positive current, positive voltage, this is where the power is being generated. And the operating point for the curve has to exist on this line. So if you open circuit it, it would operate at this voltage without any current, zero current. And if you short circuit it, then it's going to operate at this point where it's zero voltage and then the full current. And if you kind of calculate the points for all of these, there's one point where the positive power is the highest value. So this would be right here. And this is called the maximum power point. So if I say MPP, that means the maximum power point of the curve. So we want to operate at this point because this is where the PV produces the maximum amount of power. And so if they're all the same, we would simply pick that one current, and they all operate at the same exact maximum power point current. So we optimize all of them at once, and we extract every single bit of power out of every single one. That's the ideal case. In real life, it's going to be a little bit different. Let's take the case where one of these cells is a little bit degraded. So this is, for example, either a little bit shaded or it's degraded in some way. So it doesn't produce as much power. And if you notice the difference, so this is the IV curve for PV3. And if you notice the current characteristics are shifted down. So it's the same curve, but just shifted down a little bit. And if you go back and recalculate the maximum power point for this one, it's going to be, for example, on this blue dot, it's at a lower current than the other ones. And so to maximize the overall string, since they're all in series, there's only one string current that you can choose for the whole string. When you're maximizing the whole string, the optimal current will actually be in between these two. So it's going to be lower than this maximum power point for PV1 and PV2, so a little bit lower. And for PV3, it's going to be a little bit higher. So right away, we're already losing some power. We're not able to maximize each of these at their maximum power point. We are losing just a little bit. Maybe it's not that severe, but actually if you have a lot of them in series, you're going to be losing some of that power. If the problem becomes more severe, then we're going to have actually this is severely shaded, for example, shaded or degraded. The current characteristics move down even further. And if the current for the whole string, for example, were here, it might be that the power through this PV is actually going to be negative. So this is where it would be acting as a load. And so it's sinking power actually rather than producing it. And the reason you would operate at this current is that these two are providing so much power at this current that it offsets the lack of power that is produced in this one. So this can happen and does happen in many PV systems. So because of this mismatch in series, this can lead to long-term reliability problems, degradation, and heating. So these are all kind of the problems that the mismatch in these strings can cause. And now we look at how can we solve this using converters to try to offset this mismatch while still providing maximum power to the output. So now we're going to go into overviewing PV differential power processing converter concepts. And I want to start with a little bit of history. Not that much, it's not that far, not that old, but the first paper that we've been able to find that has this specific idea that's applied to photovoltaic panels is this paper in 2001 from Dr. Shimizu and his colleagues in Japan. And they called this type of circuit a generation control circuit. So generation of the PV, they're controlling that generation using converters to achieve that. And so that was back in 2001. And that idea has been out there, but in about 2013, our group, one of my colleagues, Pradeep Shenoy, and then other students when we were at the University of Illinois and our advisor, Philip Krein, we got a project working on this government grant, and we started calling it at that time differential power processing. So that's the term that I've been using in my literature, but also it can be called partial power processing because you're processing a part of the power rather than the full power. It's also been called the PV balancers and PV equalizers. So if you look up the term, you may find different names for that. And if you're interested in more variety of topics, I can point you to one of our papers that looks into that, a review of DPP techniques published in 2019. So we'll go into some of the details for that, but if you want more details, I recommend this paper. Okay, so how does it work? How does the differential power processing work? Let's start with the traditional solution that power electronics we've used in power electronics. So the idea before was that we have a string of PVs and we put them all in series and we connect them to one inverter, so DC-DC converter and then inverter, and that provides all the power from the PVs to the grid. But you have that problem of mismatch, so if any of them become mismatched in some way, you're going to be losing power. the initial way is to break them all apart. So break up all these PVs, disconnect them, and then have them independently controlled. This one, for example, is a DC optimizer, and then you can take that power, individually control it. So for example, you may have a boost converter or some sort of converter here that takes that power and then provides it to a higher voltage that goes to the inverter. This does allow for independent maximum power point control. So each of them would be able to operate at the maximum power point, which is maximizing the generation. But then all of the power that's generated, so for example, if it's 100 watts, must go through a converter that's rated at 100 watts. So all of the power, 100% of the power is processed. And so you're going to lose power proportionally to the 100 watts that goes through it. So the rating of this has to be 100 watts, rating at the panel level. And the maximum output is proportional to the efficiency of your converter. So if this converter is, for example, a very high one of 98% efficiency, then that's the highest you can get. If it's lower, maybe 95, maybe lower, then the maximum power efficiency you can get is that same value. Differential power processing looks at the idea of a hybrid between these two. So the idea is to keep the main power through the PV, like here. So they're still connected. You still use connections between the PVs, like the series string. And you have the converters that essentially make up the difference. So most of the power, the bulk power, should be going through the panel, the PVs themselves. And then the converters can act as a way to take away extra power if that PV has more power than the other ones, or to add power around it if that PV is weak. So this allows for sub-panel level control. So you still get the independent maximum power point tracking, but you don't process as much of the power. So that's the differential part in this string, is that you're only processing the difference between the main power and then the one power of the PV. So that's the differential part, and then the power processing is you're only processing the smaller amount. This allows, in concept, to have lower power rating. So you don't have to rate it at, for example, 100 watts. Maybe you can rate it at a lower value. And that's actually one of the questions we looked at. So I'll talk about that in a minute. And this allows for higher output than DC optimizers because you're not processing as much power, so you don't have many losses. So the short version is you're able to get the individual control, which offsets the power problem, the mismatch problem, but you're not wasting as much power through the converter. So that's the advantage of this topology. So there's multiple ways to approach this in terms of architecture. And here, when I say architecture, you can also think configuration. We're not looking inside the box yet. So this is the converter. We're just saying it connects from one side, the PV, for example, here, and this one, the output, connects from ground to the high voltage bus. So this is the PV to bus configuration. And this is one way of shuffling power between the PV element itself and the bus. So you can either provide, if this is producing more power than the string, this converter can push power from the PV to the bus. And if it's the opposite, if this PV is not producing enough power, enough current compared to the string, then the power can be processed from the bulk resistor, kind of this bulk, not resistor, excuse me, the bulk capacitor here that's storing energy, and you can push it through here to equalize the system while it's operating. The second architecture, there's one more, but we're going to talk about it a little bit later, is the PV to PV. And this is where the converter itself is actually connected from one PV you can think of as the input, and then the adjacent PVs you can think of as the output. And these are kind of daisy chained or laddered between. So this one, this converter, this is the input, this is the output, for example. And then this converter, this would be the input, and that would be the output. So you can kind of control each one of them. So each converter controls one of the PVs, and it's able to operate and push power in between adjacent PVs and control the system that way. Let's look at an example. If this is not quite visual, it takes a little while to visualize and understand all these. So let's go through an example, and hopefully that will help. Here is a number of PVs that we have some examples. So This is 50 watts, it's kind of the nominal PV4 and PV1 here, 50 watts. PV2 is a little bit higher, and then PV3 is a little bit lower power. And for simplicity, we'll make all the maximum power point voltages the same, and we're just going to change the currents have been changed proportionally. So each of these, in order to operate at their maximum power point, needs a different current. If we put them all in series, and here we can put a bypass diode on each of them, then we get this kind of power curve. So this is the power that's produced, and this is the string current. String current is this current here. So if we sweep the string current, we're going to have these multiple peaks here. So this is one of the peaks at a lower current, and then we have another peak here, and then another smaller kind of a peak here. The total power produced by the PV is only 183. And if we go back 1 second, sorry, the total power for the system should be 194. The important number to look at is down here in the output power. So in this situation, if you just put them in series, there's zero power process because there's zero converters, then the output will be a little under 95% efficient. This is all ideal. We're just doing this to compare the power process and the output power that we'll get. So next, let's look at DC optimizers. So what would that produce? These are all independent. So you would have 4 independent IV curves here, which are shown down here with the yellow and stars. The PV power produced, assume that they can get exact maximum power point, but you're processing all of the power. If we say that this is highly efficient, say they're 98% efficient, which is pretty high, then we would process 3.9 watts and our output power would be 98% of the input. Now let's look at a differential power processing example using, this is the PV to bus architecture. So here, and I'll just run through it here just to show kind of the currents that are happening here. So the maximum power point, this substring current actually here, this should be 5 amps would be the one that optimizes the whole string. And in this case, this one's already producing 5, so this converter could actually just turn off. It doesn't need to do anything. But this one is a little bit weak. So this converter would take power from the bus, and you can think about it as like putting it around this. So it supports this PV. So this PV can operate at 4.2 amps, and the other 0.8 comes in from the converter. This PV2 is going to do the opposite. It's producing more power than the other ones. So that 0.2 amps is going to come out actually and go directly to the bus to be provided to the load, rather than being forced to go through the string. So this is also able to be optimized at its maximum power point, while most of the power is going through the string, and only a little bit, so these currents are pretty low, are going through the converter. If we do the numbers on this, let me look at this, show you this real quick. This is comparing the series strings. This is the one we just looked at. This is the power processing. This is a little bit confusing because it's ideal. So actually at any current, so if you tell me any current, then this value, this substring value, it can actually optimize all of the PVs at that level, but it's going to process a lot more power if it's at a different value. So for example, if that string current were 2, it could optimize it, but it would need to process a lot of power, which would take away from your output. So you would want to operate at the point that is the lowest power processed for your system to optimize the output. So we assume that we operate here, which happens to be the 5 volts, which is the example we just showed on the left. So for that point, the power process would be only 10 watts of power rather than the close to 200 watts. And let's give these converters a lower efficiency just to kind of emphasize the advantage of this approach. Let's say it's only 90% efficient. Then that would be 1 watt of loss, and still you end up with 99.5% efficient. So let's also look at the PV to PV just for comparison. And I'm not going to go through all of these just for time's sake, but this is a little bit more complicated to go through all the numbers, but if you add up all of them, each of the PVs is able to operate at their individual point, and the power process through each of these converters is going to be lower. So this one again is also operating at its maximum power point. This is the point that it operates at for the whole string. And you can see immediately that it's higher than the series string. And the power processed, if we go through and calculate that, it would be about 8 watts. And the losses, even if we assume it's about 90% efficient, would be 0.8, which ends up being 99.6% efficient. Again, this is all ideal. This is for just comparing. So of course, you're going to have a lot more losses in your system, but just giving you that caveat. So how do we kind of digest these different ways? How do we think about them? So to compare these different topologies or different architectures, we can do a figure of merit. And when I was doing this analysis, the simplest way is to do just series string without any converters. So that uses the baseline. So the series string, the power that you would get for series string in a specific case is the baseline power. And then the power out is the power for that specific case. So for example, the DC optimizer or the PV to bus or PV to PV, then that's a power out for that. So the DPP power over the power you would get with the series string. So that gives you how much of an improvement you have over a series string. So if you have that equal to 1 would be exactly the same performance, and then greater than 1 would be better. And so we want to have a higher value here. This is from the paper down here. This has a lot more analysis, but I just want to show you the results. And so if we go through the DC optimizer, and this is a figure of merit, I believe at 25 years after the system has been operating. Oh, maybe. Oh no, this is for a specific case. So this is the DC optimizer. It would be better, but the other ones are actually going to be better. So this is the PV to bus with no limit, meaning that it's kind of ideal. The converter can process any amount of power to maintain that maximum power point. Then we get a big improvement with these two, the PV to PV and the PV to bus. But if we add a rating, so we say it's not rated at 100% of the panel, it's rated at only 8% of the panel. So in this example, rather than a 100 watt converter for a 100 watt panel, you only have 8 watts of converter for an 100 watt PV panel. Even with that, we can get a very big improvement. All of these, notice, are higher than the DC optimizer. So with smaller converters, we can get a higher performance over a range of mismatch conditions. Okay. We looked at this for a lot of different conditions where we knew these cells over time in a panel are going to become more disparate. So they're going to decrease in power, and they're also going to become more different. So as they degrade over time, the variation will be larger between them. So we looked at the variation that we expect at 0 years. So there's still some variation even with new panels. And then the variation we would get at 25 years. And this is assuming no partial shading. This is just looking at degradation in the panel itself. And after doing some studies, we found that the rating the end result, the rating that would work for the system over 25 years, if we use the PV to bus, could be around 17%, for example. And for the PV to PV, the rating could be about 33%. So if we had a 100 watt panel, the PV to bus converter would only be needed to be rated at 17 watts, and the PV to PV would only need to be rated at 33 watts. And you would still get a very high improvement over 25 years. So at 25 years, this seems not too significant, but it would be, for example, 5% better, 6% better, 6% better. What that equates to is the DPP converters can provide 2.8% performance over 25 years. So if we kind of look at the overall lifetime, this is the figure of merit for the lifetime over those 25 years, then you would get 2.8% power increase, energy increase over that time, which may not seem very significant, but actually over 25 years of power from one panel, 2.8% is going to be a lot of power. So you're going to increase just a little bit, but over many, many years. So that is actually a pretty good improvement. And it also allows for individual control. So you're more likely to not completely bypass that one cell that's shaded, for example. So the hotspot risk is also reduced because you're able to control at a submodule level. So let's summarize this part. So based on these studies that kind of look at the full system, DPP has advantages over series and over DC optimizers. So it has potential to do better and have more power output because it has lower power processed, but yet yields a higher output power. The general ratings we found for a normal size system is about 33% or lower can be rated. You can rate your converters at that level and still expect to have a high power yield, so up to 2.8% more energy over 25 years. And if you had a higher rating, you could actually compensate for even more significant mismatch. So for example, severe shading, you could compensate for even more. So I'm going to continue on now to the part where we're talking about the individual topologies. So what goes inside of those boxes that I showed, and hopefully for people who are more familiar with the topologies, that will kind of help you see how they actually are operating. So let's go into the converters, and I'm going to speed up a little bit because I think I'm taking too long. Okay, so let's talk about the topologies. In the PV bus, which we discussed earlier, the flyback converter is the most commonly explored one for that use that's been implemented. So this one is connected from the input of your flyback would be the PV, and then the output would be the whole string of the PV. So if there's NPVs, it's going to be that NPV voltage. Because the input is in series, so these are all series, but the output is in parallel, you need to have an isolated topology for this. So because of that, the flyback is very commonly used. And one thing to note is that this output voltage is going to be kind of high. So how would that work? The main power is going through your system, and you're going to be shuffling power in both directions. So it does need to be bidirectional. And for example, when we're going from power flow from PV to bus, you would drive this Q1 as your main switch, and you could either use this as just the diode in the MOSFET, or you could attach another diode over it, or you could do synchronously. We've actually just implemented with using the bypass diode of the body diode of this second MOSFET. So that would be flowing in one direction, and then to flow in the opposite direction, you would do the opposite. So you would drive this one, and that creates the current flowing in this direction, and then it's going to flow out to the PV and provide extra current through this string. If you want to get into the equations of it, it's a little bit complicated. This system is pretty highly coupled, so control is going to be one of the more challenging parts of implementing these, particularly this, the PV to bus topology, because you have this substring current, which is going through here, but then you also have this return current that's coming out through the converters, and then those two together will be the string current, which is what actually goes to the inverter. So the string current is what's controlled by the inverter, and then these two others are going to be determined by the PV system and also the controls of the converter. So these are the different equations. It's actually just using KCL and KVL, very basic equations. It's just many terms, so sometimes it can be a little confusing. But I went through and I simulated a bunch of these situations. So given a specific power, and we compared it to a series string. And this one is actually a little bit confusing to understand. The string current is actually only going to be seen, this is the string current that goes out to the inverter, it's only going to be within a very limited current that there's valid solutions. So in the ideal sense, you're only going to get solutions at this, this very narrow range, which means that if it's just truly ideal, you can't really sweep the current, but in implementation, this is actually not a problem. So, but you can see here, if you are able to reach this ideal power, it's definitely higher than the series string case. So when you limit the power, so this is, for example, a 2 amp current limit. So now the converters can only provide up to 2 amps to the PV panel. We have a little bit of a different curve. I'm going to point you down to this one where we're looking at the output power versus the string current. And we get some effect of the rating limiting. And then we have some ideal, this is where we're in the ideal range. In implementation, this actually comes out smoother. So luckily this isn't a problem. It's just in the calculations for the ideal case. So let's go on to the PV to PV. This one has been much more explored in the literature, and probably because it's less complicated to control. But the converters down here are usually a switch inductor. You can also think of this as a buck boost, and the resonant switch cap converter. So there's been multiple groups that have worked on this. The positive part about this is that you can only rate this voltage at the PV level, and you don't have to rate it extremely high voltage. For example, it doesn't have to be the bus voltage. For example, if the power is flowing from the top PV to the bottom PV, you could, in this direction, you drive it in this way, and you can synchronize these switches, and you get power through the inductor going this way. And you can kind of see this is similar to a buck boost converter, just to show you the difference. So this would be PV1 is like the input voltage here, switch 1, the inductor here, and then this diode becomes an active switch here, and then this V out is like the second PV. So you can think about it like that as a buck boost converter, and that will probably help people who already know how buck boost converters work. We go in the opposite direction, so just a bidirectional, and this, in this case, the inductor will go in the opposite direction, and it would be like power flowing from the output side to the input side. The governing equations for this are actually quite complicated in that they are coupled, but it's if you're trying to calculate how to do this in simulation, it gets a little bit complicated, but when it's implemented, it is not as bad actually. So you would use these calculations to determine the duty ratio, and then all of these duty ratios can be put into this matrix form, and the DPP currents are these currents from each of the converters, and then these are the individual PV values. So you can use this just for the calculation of the system. When it is, there's no current limit, meaning that the DPP converters can provide any amount of power, then we get a nice curve here. So this is a, the power curve is the dotted black one here, and this is convex. This one is nice because it's very clear to see where the inverter is going to operate. So if you have an MPPT, maximum power point tracking, running, it's going to seek the maximum point. So if there's a nice convex shape, it's going to go right towards the top of that. If you have, for example, these kinds of shapes with the different local maxima, it can get caught at a lower power level and actually reduce the total power produced. So these also help to reduce the multiple peak problem in traditional PV systems. If we look at what happens when we current limit, then actually this one we had to current limit to a very small amount, and we can get a little bit of local maxima that happens, but that was at a very extreme limit. So generally, even with a normal, for example, 2 amp limit on the input current of the flyback, or this is the buck boost converter, then we're still able to get a very good characteristics. The third topology I wanted to talk about is called PV to isolated port. And this is connection between the PV and an isolated port, or it can also be called a virtual bus. It's an isolated bus that is not the same as the PV bus. So it's its own voltage, and actually that voltage can be controlled. So it can be a lower voltage, it can be around the same value as PVs, and it could actually change value. So you could design what value that voltage would be. You still need a isolated topology for this. So you would use flyback, and this has been implemented only by a few groups, but almost always with the flyback converter. Again, this is bidirectional because the power can go in and out, but it's just exchanged with this power bus voltage. And the other thing that's a little bit different about this one is that the power here into and out of the bus has to be balanced. So because it's not going directly to the load, the power into and out of this bus has to be balanced. Otherwise, your voltage is going to either run away to a high voltage or it's going to go to zero. So the control on this has to be a different type of power balance. Usually people use a voltage mode that is able to power balance the system, but you actually are not able to reach the true maximum power point for this. So it's limited, but it provides advantages in that the output voltage here can be lower, so your rating on your output of your converter can be lower. All right, and this works in the same way as the other flyback converter. The only difference is that you're taking the power into or out of the PV and exchanging it with this isolated port. Okay, so same bidirectional operation is needed. If we look at the current limit or no current limit situation, so what does the IV curve look like? The string current versus the output power. For the PV to isolated port, we have, again, a very nice convex curve here. And that's what we're looking for optimizing, consistently optimizing the power from the system. So those are all good characteristics. Even if we limit it to about 2 amps, we still get a very nice convex shape. So that's very positive for interacting with the inverter. So we went through a lot of different ones. So I just wanted to compare the different architectures. So the PV to bus. Generally, we found that it has lower power process if you have a larger string and you're able to get the true maximum power point. But you have very high output voltage. The control is a little bit complicated. It's not really scalable. So if you wanted to do higher voltage, you need to redesign your system. And it doesn't necessarily have a good inverter interaction. The PV to PV, you have a lower voltage rating, so that's a plus. You can get true maximum power point. And the rating is rated at the PV, so you could actually scale up your system. So the actual converter is scalable. However, it has higher power processed than the other ones. It's also difficult to control because it is a little complex and it doesn't always have good inverter interaction. The PV isolated port has good voltage rating and good voltage balance. Voltage balance is the way to implement the control. It's relatively easy. It is scalable and it has good inverter interaction, but it's not able to reach true maximum power, and a little bit more power is processed through it. So these are different options that you could look at if you're trying to implement these. It's not like one is completely better than the other one. It depends on what your system is, what kind of mismatch you're going to be expecting, and what kind of implementation you would need. So these all have advantages and disadvantages. And if you're designing this, you can consider what would be most appropriate for your system and your design constraints. I wanted to wrap up with just sharing the results from some of the work that our group has been implementing. We call it segmented differential power processing. And I'm just going to go through and jump to the results so that I'm not going to give lots of details, but I want to give you a sense for what you can actually achieve with the results. So this is a system that we worked on. I worked on it when I was working in Korea with a company. Project was funded by POSCO, and they were looking at a building where they wanted to put PVs on the wall, but they wanted to be like a pattern. So they wanted to have different colors over them. So inherently, you're going to have mismatch between these systems. They're also going to have shading from this part of the building on the PVs. And so it's a very good case for mismatch. Okay, so The idea here, we looked at the PV to bus, which I explained, and I hope you kind of got the concept. If you have a really large, many PVs here though, this voltage is going to be really high compared to the voltage of the PV. So for example, if you have 10 or even 20, you're going to have really high voltage. You're also going to have a lot of wires that are going to connect. You have to connect all together. So that can be really messy. So we suggested a segmented differential power processing topology, where we essentially segment them into smaller units, and those units have fewer connections in between them, and they interact with each other. So for example, these 4 PVs, they can exchange power with each other. They have a bus here, and that bus can actually exchange power with the whole string or with the individual PV panels. So with this concept, we looked at a few different ways to implement it. We looked at how having a converter here, that this converter's job is to regulate the bus. So you can also think about this as a hybrid between the PV to bus, which is the first one we talked about, and the PV to isolated bus, which was the last one that we talked about. So this one kind of has a converter that can control this voltage and also take power from the overall bus and then to this lower voltage bus here. But we actually found that we could take this converter out, and as long as you controlled it correctly, it was able to automatically adjust the power so that you could make this bus here the output of these 4 PVs, and then you could string them together and actually get a full system that works. So we went with this type of topology or architecture, and we use the flyback to achieve that, a bidirectional flyback. So we have 4 of these in one board. And first we wanted to see the efficiency we could get just with the flyback. And we're looking at the forward direction is in blue, so at full load, and notice this power is only goes up to 25 watts. The panels were closer to 150. They were custom panels, so they're a little bit lower power, but we were able to have very good performance even at just 25 watts. So at that full load, with the sensor losses, so a self-sustained system, we got about 98% efficient in the forward direction and 85% efficient in the reverse direction. The positive part is that we'll be able to achieve higher efficiency than that in our results. So we looked at a shading condition, and we want to say, as we increase shading, how does this affect our system, and how does this affect how much power we can get out of it? So we're going to compare the series string and the DPP, segmented DPP system that I just mentioned. And the important metric we're going to look at is the system efficiency, and this is different than the flyback efficiency. That would be actually the module efficiency. We're looking at the PV produced by each of the PV panels, so what is produced at the beginning, and then the total power out of the system. So this is the system efficiency. That's the number that we are going to care about. So this is the different shading levels we looked at. So we shaded from no shading, so I know this is a lot of cases, no shading, and then we incrementally shaded, increased the shading until over 60% shading of one of those panels. And so you can see the linear decrease of that 4th panel is decreasing. This is the green is the PV power. And then on the bottom plot, this is the series. So we just put them in series, and you can see we have multiple peaks forming after a little bit of shading, and you can kind of see where the maximum power point is going to be. And then the blue one is what we were able to achieve with the segmented differential power processing converter. And you can see in each case they are higher. And let's just put that in terms of efficiency and power so you can see what that is. So this is the level of shading. So that example I just showed, just plotted on a different plot. So first we're looking at system efficiency. Even when the series string goes all the way down to 80% efficiency, with the DPP system, we're able to maintain it always above 92%. So actually this is a pretty significant increase across the board. And even when there's no mismatch, it's just under the performance of series string. And if you look at this graph, this just shows you the power levels that we're actually getting and how the DPP always has a good improvement over the other one, and it's comparable right at that equal shading level. So we're able to have high system efficiency and generate very good power, high power, even in shading conditions. So I'm going to wrap up. I think I took a little more time than I expected, but just to reiterate what I talked about. We talked about PV mismatch and how it's caused by manufacturing, dusting, shading, things like that, and how we try to get rid of as much mismatch as possible. But we can use power electronics to try to get, even with that mismatch, to try to optimize as much power as possible. And DPP systems are very good for that because they have very low power process, but are still able to do individual control and get a high power out. They're appropriate for high voltage applications. For example, grid connected systems are very good for that. And they outperform DC optimizers and series string. So in both cases, they're going to show better performance. The power ratings approximately can be about a third or lower and shows pretty good high performance throughout the whole lifetime of 25 years, and it can yield some higher output power energy over that time. The segmented DPP topology that I talked about mostly looks at how to improve modularity and scalability and just ease of implementation. And it addresses the high voltage problem that we get with the PV to bus. And the results show that we're able to get 96% efficient at even lighting conditions, which is comparable to the series string. But in heavy partial shading, we're able to get maintain over 92%, which is very high compared to series string and actually very good compared to DC optimizers. So that is my presentation. Thank you very much for listening, and I'm happy to take questions.
So, thank you, Professor. Eldo?
Yes, sir.
So now it's the
Yes.
time for Q&A.
Yes,
So you can read out the questions from the chat box.
Okay, sir. We do have a couple of questions to start with. The first one, for simulating the converter circuit, which simulator is used?
Okay, for simulating the converter circuit, I used two different systems. So for example, in the simulation plots where we're doing just the, let me see, oops. Trying to show an example here. For these, for example, I actually use MATLAB and I do everything in calculation for implementing each of them. So I use the equations that I have in each of these. So I'm implementing these all at the parameter level. So those are done in MATLAB. Those are all ideal calculations, and you can factor in, for example, losses based on a factor. And then for the larger systems, the actual implemented systems, like the segmented DPP system, there we used MATLAB, and we tried also with PSIM, but we used MATLAB Simulink. So we actually did it in Simulink to ease up control implementation, and we were able to get the results. It just takes a long time to simulate, so that's a big negative. But you could also do it in PSIM. We had trouble with some of the larger systems in PSIM, unfortunately.
Eldo?
Hello. Hello.
Yes, Eldo. Please.
Yeah. Good evening, ma'am. This is Yugal Kishore.
All right.
Actually, I want to work in a multi-input, multi-output DC to DC converter, especially designed for the DC homes in rural area. So, what is your opinion? Like whether I will go for it or not? Like multi-input, multi-output DC to DC converter.
What kind of, are you talking specifically about a PV system or a renewable energy? And then what would be your load?
No, ma'am. I'm only concerned with the PV systems only. Input is PV system. Suppose I'm having multiple PV system at houses, and like the load requirement of the different houses is like different. So I want to connect, I want to interconnect all those PV systems.
Okay. Let's see. If you're doing is it a DC grid by chance?
Yes,
Then?
ma'am.
Okay.
Yeah.
Let's see. I would have to think.
Actually,
There
I
you're
have
going to
gone
be.
through, ma'am. Actually, I have gone through many literatures, but I didn't found such kind of system. So I want to know whether it is feasible or not. Like,
Yes, I think the answer is it's definitely feasible. I think one of the challenges with that, especially if you have a DC grid with only a set amount of loads, is the power balance. So you want to match the power provided to the loads that you have, and the loads may be changing. So you need a kind of a full DC grid and a good control strategy for that. Oh yes, I feel like this is a problem that would have a lot of potential solutions, and I don't know if I have a specific answer for you, but you
okay.
would need to look at.
So is it possible to control? Suppose I'm having 4 different systems, like 4 houses I have, and every house, let us assume the rating of the PV panel is 250 watt. So, like, is it possible to control all those the load of all those 4 houses with the help of single DC to DC converter?
Um, it's probably you're going to want to have multiple converters, and I I think that the go-to way would be to have individual converters for each of the PDs, and
Okay.
then a converter to the load, and to be able to control the amount of power that each one is providing. So in order to match the power from the PVs to each of the loads, and you would also need a way to, if the PV power provided cannot meet the load, it's too low, that the system either sheds a load, gets rid of it, or is they somehow able to adjust, or otherwise it would shut down completely. So that's really a control and a power balance problem, which is you can use conventional converters, but the control of the whole system is going to be more complicated.
Actually, I want to work for the DC homes for rural area. Like I belongs to Chhattisgarh state of India, where we have remote villages. They don't have access to the electricity, and if we go for what we call inverter-based PV systems, then the cost is very high, and
Yes.
the requirement is very less. Like they need only 2 LED bulbs and one fan, and that will be done by one BLDC motors. So I want to work for that only.
Actually, this is very similar. I didn't discuss it in this one, but let me see if I can go back to, I don't think I have a lot of material on it. It's actually a similar problem to what we're doing with the mobile power electronics. So this is a similar idea in that you have individual, so each PV has its own converter, but would be like a parallel differential power processing concept, but you can actually control each one individually. And so you would have one converter for each of the PVs, and then you would have to monitor this voltage. This is a load voltage that goes out to your loads. If this voltage starts to become too low or too high, your maximum power point tracking, the algorithm that runs these PVs, can adjust. So if the voltage becomes too high, you can change the algorithm to reduce the power coming out of this PV to match the load exactly. And you do that based on the voltage that's provided at the DC voltage that's going to the loads directly.
What about this cost of this DPP configuration?
This one would be very low, actually. We're looking into actually the one shown here is a separate converter. We're also looking at, essentially it's a type of buck boost converter, or very similar to a boost converter. So this one I think would actually be a lower cost solution, and you would not need an inverter. But if you have multiple voltages, you may have to either have 2 voltage rails, or you would have 1 voltage rail and then you would have 1 step down voltage, 1 step down converter to go, for example, 12 volts and 5 volts or whatever you have.
Okay.
So maybe this would be useful to you. We're still publishing it on.
Ma'am, is there any scheme in your institute by which Indian scholar can work for the short period?
It's possible. Yeah, maybe you can email me separately. Let me just put my email. I'll put it in the meeting here. I'll put my email here and you can email me separately and we can see if there's any.
Professor, we will post it in that chat box,
Okay.
your mail ID.
Great. Yeah, so please feel free to
Okay, Eldo, is there any other questions?
Yes, sir. There are more questions.
Please.
1 second. What studies did Professor Catherine did to explore the year's reliability of DPP architectures?
the reliability or
Reliability.
reliability. This is an excellent question. So we have done, let's see, I'm trying to find one that I can show. I think even just this. The reliability, we've done some initial reliability studies, and that was all theoretical. However, the one advantage that, well, there's multiple advantages, but in a traditional system or a DC optimizer system, if one of your converter goes down, essentially your whole PV would be lost. So the reliability, the breakdown fault condition is usually not very good. In the DPP systems, if this converter goes down, unless it shorts across, then it's not good. But if it shorts open, you essentially, if all these failed open, then you still have a string. It's essentially the same as a straight series string. So the fault condition, for example, is going to be better in general. We still have to do studies to get the exact numbers, for example, but the reliability should be higher. Also, because this is processing lower power, they're not going to have as much heat through the converter, and heat is one of the big contributors to making the system fail faster. So in terms of wear over time, these systems are processing lower power, so they should be more reliable than a full DC optimizer, for example. I think that's, yeah, those are the things we've looked at so far.
Next question. What kind of MPPT algorithm used to perform the control of a DPP?
Another excellent question. So in our implementation, let me try to jump to a slide here. I didn't cover it here. This one is, the fundamental idea is a maximum power point tracking, perturb and observe maximum power point tracking algorithm. You can also do a voltage balancing, which is easier to implement in general, but you don't necessarily get the maximum power point, but it gets you pretty close. So a lot of the papers that are looking at any of the DPP solutions will either do voltage balancing, and some will do a true maximum power point tracking, but sometimes it's a lot more work to do the true maximum power point tracking once. So this one, I don't know if I have the slides for it. Oh, no, I do not. And oops, I lost my slides here, sorry. But we do a modified perturb and observe type of algorithm, and it's just a little bit more complicated because you have to go through each of them in series. You can't just change the whole system at once because it's highly coupled. So it's a slower maximum power point tracking that uses perturb and observe. So you perturb the system and then you see how it reacts, if it goes to a higher power or not, and then you keep changing the system to continually track the maximum power point of the full system. So a lot of them are based on perturb and observe because it's pretty well documented and usually keeps you right near the maximum power point.
Okay, now next question. What is the condition for power flow from a DC bus to PV?
DC bus, okay. DC. Okay, so let's go to one of these. Actually, go back to the example. This is a little bit, oh, this one. So from the DC bus to the PV, in this case, for example, this is when the string, this is a substring current, but if this is 5 amps going through here, then this PV cannot provide enough current. So when the PV that in question, the PV being controlled by this converter, which is number 3 in this case, it's too low. It's lower than the other ones, and the other ones want to operate at a higher current. So that's the case, and you can think of it as a weak cell. It needs a little bit more power to equalize the other ones. It's like too short, so you need to put in extra current to make it match the other ones. And then that's a case where we would take power from the bus, and it's kind of weird because it's kind of circulating power. Power is always moving from the PVs to the bus and then to the inverter. So it's the power that comes out here, and some of it's going to cycle around here and then provide the power to this PV. But by doing that, you're able to operate each of them at their maximum power point. So you're getting maximum power from each of them.
Okay, ma'am. Next question. How do you account this model for utility scale solar PV systems? Any benchmarking done? How does it impact in cost of the system?
Okay, so how does this apply to utility? Another excellent question. So the original ones that we worked on, so were these kind of basic concepts. So the first part of it, up to all of these different topologies, these had the challenges. Actually, I'm going to go further to show the challenge that we had. We brought these to companies in maybe 10 years ago, and we tried to convince companies, solar companies, to adapt and utilize these because they do, from an engineering perspective, have such a benefit in terms of power and ideally cost, because the converter components will be lower than, for example, DC optimizers. However, because of all the additional cabling and all the more complicated wires, because you need these interconnected cables between the different systems to transfer the power, it was a no-go. There was no traction in those systems. So because we had trouble with getting companies to buy into that, we weren't able to actually get this to a utility scale. So this implementation, the segmented one, it specifically addresses that problem of not being able to scale up. So this one is more built together, almost like some of the microinverters that would attach to the back of the panels. This would attach to 4 panels, would attach to 1, and then those could be directly connected to each other. So this concept is trying to address some of the utility challenges in that it needs to be simple for people to install, and it needs to be hard to mess up because labor costs can be expensive and you don't want to have it be too complicated. So it's been patented, but it's not yet in the phases of scaling up to the utility, but there's no reason that it couldn't scale up to a utility. And right now we assume that it can interact with an inverter that goes directly, a commercial inverter, for example. They are designed to work with that type of inverter, but you could also use these concepts in a DC bus system. So if you had a remote one like the person earlier asked about, we can also implement these ideas, but we haven't looked at those specifically. So it's a potential for that. So in terms of cost, any new projects is going to be more complicated, but because these components the ratings can be smaller, they should be cheaper than the traditional ones. And I see no reason why this couldn't be competitive. It just needs to be implemented and needs to be put to scale. So it's not implemented yet. It's still in the concept phase, but hopefully it will move forward.
Okay.
Ildo, is there any other questions?
Yeah, there are many questions. Let me read out one.
If there are too many questions, I think we can take it. Say we will send us the madam the questions via mail.
Yes, I can answer them later if
yeah, you guys
easier.
can send the mail, or you guys can tag it in the meeting link
that
sent to
mail
you.
ID is posted in the chat box, chat window. So I think due to some time constraints, remaining questions can be taken via mail, I think.
Yes, please feel free to email me and I will try to respond as possible, or point you to references that might be able to help you. So
okay,
thank you very much.
There is also a provision for asking questions in the feedback form. Do you use that?
Yeah.
Yes,
Participants
yes.
can use that also. Yeah. for asking your questions. While filling the feedback form also, you can ask questions. So that professor will reply to you via mail. Okay, Vijana madam, are you here?
Yeah.
Vijana madam, I request you to express our gratitude to professor
Yeah.
in a few words. Madam, please.
In fact, Professor Kim, even it was so informative that you were explaining, because you actually did all those experiments, and the passion with which you have done has been shown in the presentation also. I think it is highly beneficial for all those people who are working in converters. You have specifically gone through the minor details, and the references are already there, which will naturally help all of them to continue with their research. Thanks a lot for all those minor things also that you were pointing out, which actually opens up how to look at things for each of the researcher here. Thank you very much, ma'am. To your interactions in the future also, and we would even request you to come over whenever it is possible to Kerala section. Thank you, ma'am. Thank you very much.
Thank you very much, and I appreciate it, and I really hope I will be able to in the future. Thank you.
Thank you, ma'am. Thank you all participants. We had today 150 plus participants. Thank you all participants for joining us. So thank you. Thank you.
Thank you.
Thank you, madam. Thank you all. Goodbye.